Hey everyone, welcome back. This is Mr. Saracola, and today we're going to be looking at unit conversions and scientific notation. So on the screen, here is our do now. We're going to give you time to work on this and check in on the day of class to see what the answer is to this problem. Now, we understand that math is sometimes something that we struggle with. Chemistry, whether I like it or not, does involve math. And today we're just going to sort of build the foundations, build the basics of the math that you need in this class before we move forward. This way no one gets a little bit lost, nothing's too challenging, and we could just move forward from that. So to convert temperature is a measure of the energy of a molecule. We think of it as how hot something is. We have different temperature scales. And in order to convert temperatures, it's actually pretty simple. We're going to follow this formula right here. So I'm going to annotate this if it lets me. I'm going to annotate this, X this out, and utilize this formula in order to do this. So our formula is our kelvins equal degrees Celsius plus 273. Kelvin is just another unit of temperature, just as Celsius is. In America, we use Fahrenheit, but since this is a science class, we use these scientific, or these, I can't remember what the word is. International System of Units. Wow. Okay, so our Kelvin temperature, so what Kelvin temperature is equal to 25 degrees Celsius? Well, let's just start by rewriting our formula. Kelvin equals degrees Celsius plus 273. That's a terrible 7, but forgive me. So we're looking for our Kelvin temperature. So we're going to leave that as our variable, kelvins. And we know that it is 25 degrees C plus 273, and we'll end up with 293 kelvins. What Kelvin temperature is equal to 200 degrees Celsius? Well, let's do the same thing. Kelvin equals degrees Celsius plus 273. That's a 2. I'm just copying this formula down here. Okay? So our Kelvin temperature equals 200 degrees Celsius plus 273. And that will end up equaling, if I do my math right, 473 kelvins. Let's work backwards a little bit. What Celsius temperature is equal to 200 kelvins? Well, we know that kelvins equals degrees Celsius plus 273. And we know that we have 200 kelvins. So instead of plugging in for C, we're going to plug in for K, because we know that K is kelvins. C plus 273. How do we solve for this degrees C? Well, we subtract 273 from both sides. And what we end up with is negative 73 degrees Celsius. Hopefully that is clear. If not, ask about this in class tomorrow. Moving forward, let me clear all these drawings. Clear all the drawings, please. Thank you. We're going to look at scientific notation. And what scientific notation is very helpful for is representing very, very large or very, very small numbers. For instance, we've got two different types of exponents. Scientific notation is always, always, always made up of three parts. Let me get my annotations back. That didn't work. Go back. Let me get my annotations back. There we go. It's made up of three parts. The first part is a number, and this number is always between 1 and 10. If it is not between 1 and 10, it is not in scientific notation. 6.022 is between 1 and 10. Then the second part is this times. And then we've got our third part, which is 10 raised to some number. In this case, 10 to the 23rd. What that 23 tells you is how many times to move the decimal place. And I'll go over that in the example coming up. So it's always made up of three parts. A number between 1 and 10, this times, and then 10 raised to an exponent. Let's look right here. We've got 1.6. That is a number between 1 and 10 times 10 raised to some exponent. And depending on the exponent, that'll tell you if it is a really large number or a really small number. So let's look at first positive exponents. Positive exponents are things that have a number that is positive as its exponent. Straightforward enough. So we use these for really, really big numbers, generally things that are greater than 1. For instance, we've got 3.0 times, times 10 to the 5th. What this tells us is that we've got the number 3.0 times 10 to the 5th power. What that means is we've got times 10, times 10, times 10, times 10, times 10. We've got 5 tens. So you can just do 3.0 times this number, and you'll get 300,000. They are the same thing. Negative exponents are generally, or always, for small numbers, anything less than 1. And what we're looking at here is we've got 3.0 times 10 to the negative 5th. The key here being this negative sign. And if you remember in math, what a negative exponent means, is that, sorry, my pen is not doing the greatest job right now. All good though. What a negative exponent means is that you have 1 over this number. So we've got 1 over 10 times 1 over 10 times 1 over 10 times 1 over 10 times 1 over 10. Because that's what a negative exponent indicates. For instance, 2 to the 2nd power is 4. 2 to the negative 2nd power is the same thing as 1 over 2 to the 2nd power, which is equal to 1 over 4. So what this negative does is it tells you that that is in the wrong spot. It needs to move from this numerator to a denominator. If this isn't making sense, we can go over more examples in class, but basically that is the, I guess it's not a short explanation, long explanation of what scientific notation is. Let's look at how we actually use this, because I think that will become more clear. Speaking of clear, clear all the drawings. That was not a pun. I didn't mean to do that. All right, so let's look at an example. Let's say I want to convert this number into scientific notation, 240,000. Well, we know that the decimal goes all the way at the end, if it's not already there. So let's put that decimal all the way at the end. So we need to move this decimal to the left until we get a number that is between 1 and 10. So let's do that. So let's move it once. We move the decimal from the end closer to the left. We now have 24,000. Is that between 1 and 10? No. Move it one more time. We've got 2,400. Is this between 1 and 10? No. We've got 240 now. Is this between 1 and 10? No. 24. Is this between 1 and 10? No. Finally, if we move it another time, we get 2.4. We now have a number between 1 and 10. So now we ask ourselves, how many times did we move that decimal? Well, we moved it 1, 2, 3, 4, 5 times. So then our number is 2.4 times 10 to the 5th power. Let me write that out so we can all see it. Not in text, I would like to draw. So we've got 240,000, and we want to convert that into a decimal. Or sorry, into scientific notation. Another way to do this is to just physically move the decimal. So we moved it once there, twice there, 3 times, 4 times, 5 times. So now we've got 2.4 times 10 to the 5th power. If we were to go the other way, let's say we had a number like 0.002, we would do the opposite. Well, we need to get this number between 1 and 10. So we're going to move it 1 time. Is that between 1 and 10? No. Is that between 1 and 10? Still no. Eventually, we move it here, and we get a number between 1 and 10. We get 2. How many times did we move it? Well, we moved it 1, 2, 3 times. And since we moved it to the right, we get a negative exponent. Since it is a small number, a number less than 1, we have this negative exponent. If any part of this is unclear, please, please, please ask about this in class tomorrow when we go over it. Should clear this. And in class tomorrow, you will practice converting these numbers. Hope you have a good day. I will see you all tomorrow.